Welcome back to CS Connect series. We are in Mathematics for Computer Science content. From this video, we are starting the playlist Mathematical Logic. Under this, we have a set of topics, but for this video, we are going to discuss about propositional logic. What are actually propositions? In general terms, we can say proposition is a statement. At the end of the statement, you will be able to answer it like whether it's a yes or no. So any statement that will make you answer as yes or no will be termed as proposition. It's a declarative sentence that is either true or false, whether it's yes or no or true or false, but in logic context you have to use true or false, but it cannot be both. That is the thing you have to understand. So let's see few examples. When we say 1 plus 1 is equal to 2, change this statement as a question. Is 1 plus 1 equal to 2? Yes, it's true. So this is a proposition. When we say 2 plus 2 is equal to 3, we know that 2 plus 2 is equal to 4. So 3 is a wrong answer. So in that way we can say this statement is false. So even this particular expression or this particular statement we can say it is also a proposition. Now just consider this example. X plus y is equal to z. Will you be able to answer something like true or false for this? Quite not possible. Why? It's because you don't know the values of x and y. Only when you know the values of x and y, you can compute z and check whether that is right or not. See, in the previous example, we said 2 plus 2 is equal to 3. Just compare it to x plus y is equal to z. We can check whether this RHS is an answer only when we know the values of the operands in the LHS. Similarly, unless we know the value of x and y, we will not know the value of z. So this is definitely not a proposition because it will neither result in true nor in false. But can we turn this as a proposition? Yes, there is a possibility. How can we do that? If we assign value to the variables, then we can turn this as proposition. Say for example, if I give a value of 5 to x and a value of 10 to y, now you can check this. 5 plus 10 is equal to 15. Yes, it is true. When we say 5 plus 10 is equal to 20, we can say it is false. So we can change this particular expression or this particular statement into a proposition once we assign some value to the variable. Until then, it cannot be termed as a proposition. Variables are used to represent proposition. The conventional letters or the traditional letters that we use for propositional variables will be P, Q, R, S. If you have come across questions involving propositional logic, mostly you can find for 2 variable they would have used P and Q, and for 3 variable they will be using PQR, and for 4 variable they will be using PQRS. These variables are called as propositional variables, and they can also be called using the term sentential variables. From the first 2 examples we can understand there are 2 values that can be given to a proposition. It can either be true or false. This value is actually called as the truth value. The truth value can either be true or false. If it is true, we can denote it using capital letter T when the proposition is true. If it is false, we can denote it by capital letter F if it is a false proposition. Now we will get into the title of the video. The area of logic that deals with propositions is called propositional logic or propositional calculus. Both mean the same. There are 2 kinds of propositions possible. You can take it as a single statement proposition and multiple statement proposition. Say for example, when I say 1 plus 1 is equal to 2, it is just atomic proposition. It means you cannot express it in terms of simpler proposition. But if there is a statement like 1 plus 1 is equal to 2 and 2 plus 1 is equal to 3, here you can just split the single proposition as 2 proposition. One being 1 plus 1 is equal to 2 and the other being 2 plus 1 is equal to 3. Such kind of propositions are called compound proposition. So when there is a simple proposition, you cannot express more simpler than that. That will be atomic. Atomic in the sense you can take it as single proposition or single statement. So compound proposition means when you have multiple propositions. Proposition 1, proposition 2 up to proposition n. So there are multiple propositions. So for example, I just use the word and. What is actually this and? It is combining 2 propositions here. If we take this to be P1 and this to be P2, the proposition 1 and the proposition 2, we are connecting the propositions using logical operator. Logical operator are used to connect any two proposition. Between proposition 1 and 2 we have a logical operator. Between proposition 2 and 3 we will have a logical operator. Between the proposition n-1 and n we will have a logical operator. Actually, what is the use of this logical operator? They are used to connect propositions. So we also have another term called as connectives. So what do connectives actually do? They form new propositions from two or more existing propositions. So when there are two or more propositions given and you are using an operator called logical operator to combine them into single proposition, there we can call that particular logic operator to be connective. So why am I splitting logical operator and connective here is only when you combine two or more proposition you can use the term connective. But there is also a logical operator which involves only single proposition. So at that time you cannot use the term connective there. Whatever operations that you do with logical operator will fall under logical operations. So propositional logic is about all those operations. Before getting into the logic operations, we'll just understand what is a truth table. So just consider a table with rows and columns. We said there are possibilities for having more than one proposition. So every proposition will be placed in every column, and we know every proposition will take two possible values, namely true and false. The rows will represent each of the possible truth values. Say for example, when there is only single proposition involved, what are the possible values? We can say just true and false. When there are two propositions involved, there is a possibility of four values. How can you say? Let's take this to be P and this to be Q. For example, for the first true value of P proposition, we have two possibilities in Q. This Q can either be true or false. And when the proposition P is false, we again have two possibilities for Q, which is true and false. This is a combination of true and true, true and false, false and true, false and false. So this is how we are getting four rows for two propositions. But earlier, when we saw only single proposition, the values will be restricted to just true and false, because that is the possible truth value you can get from a proposition. But when propositions keep on adding, this truth table will be extending accordingly. So you should check for all kinds of possibilities. That's why we are trying with two possibilities for true and two possibilities for false. What about the last column? This will be the new proposition value. Let's take there is a logical operation between P and Q. After the operation, whatever result comes, that result is represented in the last column. So this is the new proposition that comes after logical operation. So what is a truth table? It is a table displaying all possible truth values of proposition. When P is true and Q is true, what is the result? When P is false and Q is false, what is the result? So for every combination of truth values, you have to find the result. This is how we will be filling up the truth table. Now let's get into the logical operation. So the first operation that we are going to discuss is negation. Let's take a proposition named P. When I apply negation operation, what happens? This becomes negative proposition. Say for example, if I say it's P, then it will turn as it is not the case that P. This is actually getting into a formal English sentence, but just understand we are just negating P, that's all. So if the truth value of this particular proposition is P, then the truth value of the negated proposition will be not P. This not symbol can also be represented using P bar, tilde symbol, then negation P, P dash and exclamation P, that is not P. There are different ways to represent this not P, and most often we will be using only this. The negation operation constructs a new proposition from a single existing proposition. So here we don't bring compound proposition concept, but it works with atomic proposition because it is going to construct a new negated proposition from a single proposition. Why have they mentioned here as P truth value and not P truth value? We know when there is a proposition named P, there are two possible values for it. true and false. So when proposition is true, the negation becomes false. When the proposition is false, the negation becomes true. So that's why they mention it as P and not P. When P is true, not P becomes false. When P is false, not P becomes true. Now let's see an example for this negation operation. We have a statement or a proposition, we can say the smartphone has at least 32 GB memory. At least 32 GB means it is greater than or equal to 32 GB memory. If we want to exactly find the negated statement as per this formal English statement, how should we do it? It is not the case that we have to place the proposition. The smartphone has at least 32 GB memory. But this is just more formal way of saying. So let's get into some normal way of telling it. We can say the smartphone does not have at least 32 GB memory. So this is also bringing some kind of grammatical English inside, like does not have at least. So when we know greater than or equal to is a statement, to find the opposite or the negative part, what will happen to this greater than or equal to? It will change to less than. So whenever you have greater than or equal to, in negation it will become less than. Whenever you have less than or equal to, in negation it will become greater than. So there is also another way of expressing this statement. The smartphone has less than 32 GB memory. All the three are right. Since we use it is not the case in the formal definition, doesn't mean all the statements should follow that. At the same time, since we use less than to imply the meaning of not greater than or equal to, it doesn't mean the other two are wrong. So there is a possibility that the statement can be expressed in any way. All you need to understand is how negation operator is being applied. Let's see the truth table for this negation operator. We have already discussed earlier. When the proposition gets true value, the negation of proposition or the not P value becomes false. When the proposition has false value, the not P value turns to be true. So this is all about the negation operation. It deals with only one proposition. Now let's get into the compound proposition operations. This is where actually we can bring connectives concept. What is actually conjunction? Let's take two propositions, one being P and another being Q. When we apply conjunction operator here, both the propositions are combined using the term and symbolically they use this conjunction symbol to represent it. If you remember set concept in set video, you would have come across union and intersection. What is actually intersection? Taking something in common between the sets. So this intersection can be equated to conjunction. Now what is the possible value for this particular proposition, which is now P and Q? You have two values, true and false. Only when both P and Q are true, we will get true. Otherwise, it will be false. So from this we can say, for this conjunction to be true, both conditions given must be true. It is false when one or both of these conditions are false. If P is true and Q is false, or if P is false and Q is true, even when one of them is going to be false, the answer will be false. And if both the conditions are going to be false, it is again false. So let's see an example. The proposition P states, PC has more than 16 GB free hard disk space. And Q says its processor runs faster than 1 GHz. Now if I apply conjunction P and Q, how can we express this in English? PC has more than 16 GB free hard disk space and its processor runs faster than 1 GHz. When you take it in English, it's just combining both the sentences using and. That's all. But in context of system, you are actually joining two conditions here, namely P and Q. So let's see the truth table for conjunction. As I said, when you keep increasing the number of preposition, the number of rows in the truth table will get increased. So we are just looking the conjunction truth table now. When P has true value, there is a possibility of getting true and false in Q. Similarly, when the P has false value, we have a possibility of getting true and false again. So what is P and Q? We said only when both P and Q are true, the result will be true. So when P is true and Q is true, we have true. For the rest of the cases, we have false. This is the conjunction operation between P and Q. Next, we will discuss about disjunction operation. The concept of set union can be equated to this. Let's take two proposition again. When you use disjunction, it becomes OR operation or union operation in set concept. So the symbol is denoted using this particular disjunction operator. And again here also you will have two possible values, true and false. For P and Q, we said only when both P and Q were true, it ended up with true value. But here you have some relaxation. Only when both P and Q are false, you will get false. For the other three cases, you will get true. So what is disjunction? A disjunction is true when at least one of the two propositions is true. Either P can be true or only Q can be true or both can be true. But when P is false and Q is false, you end up with false only. Now let's go for the truth table. So we have true in both the places. So we have true here. We have true in P alone. So again it is true. We have true in Q alone. Still it is true. But here we find false in both the places. So we are ending up with false. Let's take an example. Students who have taken calculus or computer science can take this class. So just split the proposition. Students who have taken calculus can take this class will be P. Students who have taken computer science can take this class will be Q. When you merge them together, it will be students who have taken calculus or computer science can take this class. So this is how we will be combining. Students who have taken both calculus and computer science can take the class. This is the case where P is equal to true and Q is equal to true. Students who have taken only one of the two subjects can take the class. This is where when P is equal to true, Q is equal to false, or P is equal to false and Q is equal to true. So the first three rows conditions are given in the form of meanings here, split up from the example that is given. Now what are we actually doing here? OR operation. This disjunction is also called as inclusive OR. It means you are including either P or Q or both the P and Q's existence to make it true. So this is called as inclusive OR. When we wantedly show you that this is called inclusive OR, definitely the next operator will be exclusive OR. So inclusive OR is disjunction. What about exclusive OR? Let's take the same example. Students who have taken calculus or computer science but not both can enroll in this class. It means at a time only P can be true or Q can be true, but the first row where both P and Q were true will not work for exclusive OR. That will give you false. This is exclusive OR. So from the example, let's see the meaning. Students who have taken both calculus and computer science course cannot take the class. Only those who have taken exactly one of the two courses can take the class. They are trying to establish that when P is true and Q is true, the answer will be false. We have two propositions P and Q. When they undergo exclusive OR operation, it is like P or Q. So the result of P or Q will be applied, but not both. It means when P and Q have the same values, they turn out to be false. So that's why they say exclusive OR means it is P or Q but not both. So when it is true, only when exactly one of the proposition is true, the result is true. When both are false or when both are true, it means when P is equal to T, Q is equal to T, or when P is equal to false and Q is equal to false, it will give you false. The exclusive OR of P and Q is true when exactly one of P and Q is true and is false otherwise. Now let's see the truth table of exclusive OR. So wherever you have same value for the preposition, you end up with false. T and T will give you F, F and F will give you F. What about the in-between rows? Here only P has true value, here only Q has true value, which is exactly matching with the condition that exactly one of P and Q is true. So in those cases, we will have true as the result of exclusive OR operation. So in inclusive OR, when P is equal to false and Q is equal to false, the result is going to give you false. In exclusive OR, this condition is right, but along with that, even when both are going to have true value, it will give you false. So that's why we say P or Q, but not both. Basic logical operations are actually and, or, and not. When you study about OR, you should obviously know it is inclusive OR. So definitely there is an exclusive OR. So we have come across 4 operations. Now we are getting into conditional statements. Let's take a proposition P. Now this is going to be the hypothesis, we can say. It is just called a premise, or we can say it's an antecedent. So whatever term you use, all mean the same. So we'll take a proposition P, which is the hypothesis, and we'll take a proposition Q, which is the conclusion or consequence, we can say. What about the conditional statement? We use this implication operator here. This is called as P implies Q. So when it is false, whenever P is true and Q is false, at that time only it is false. The rest of the cases it is true. So this is little bit different from the logical operations that we were seeing so far. So instead of taking this to be P true and Q false, just connect it with a term there. When the hypothesis is true, they want the conclusion to be true. But when the hypothesis is true and the conclusion is false, at that time this conditional statement will turn false. So we are not worried about the false hypothesis. It means when P is equal to false, Q can either be true or false, that is not an issue. But when P is true, Q must be true is the only condition. So when P is true, Q must be true. If P is false, we don't care whether Q is true or false. So that is the case of this particular conditional statement. A conditional statement is also called an implication, and that's why we term this as implies operator. Q is true on the condition that P holds. In what way can you express this P implies Q? There are lots of phrases for this. We can tell them if P then Q, if P comma Q, P only if Q, Q if P. So this if P comma Q is written in this way. Q if P, Q whenever P. Just write it another way. Whenever P is true, Q should be true. Then we have Q when P. So when P is true, Q is true. A sufficient condition for Q is P. Then we can say P is sufficient for Q. It means when P is true, definitely Q should also be true. Q is necessary for P. Then we have a necessary condition for P is Q. These two terms actually mean the same. Q follows from P. So if P is going to be the hypothesis or the premise, the conclusion will follow that. Q unless not P. Everything will be represented using P implies Q notation only. Let's see about Q unless not P. What is this not P? When not P is false, then Q must be true. This is actually the direct meaning. What is actually not P? They have given it as false. If negation of P is false, then what is P? It is true. So this can be translated as if P is true or not P is false, then Q must be true. So this is the condition that they have given for true value. When P is true, definitely Q must be true. The other way of expressing this P is true is what they have mentioned, the negation part. When they have negated it as not P, they have negated true as false also. These are just other ways of expressing. When the negation of hypothesis is false and the conclusion is true, that will also indicate P implies Q. What is this actually not P or Q? When we say Q unless not P, when not P is false, then Q must be true is the condition. So when not P is false, Q is true. So we term it to be true. But here when not P is false, we are contradicting this statement. We are marking Q is equal to false. So what happens? This particular result is false. Now what about not P is equal to true? We don't mind. When P is equal to false, We are not worried about Q value. Similarly, when negation of P is going to be true, we are not worried about the Q value. All the three statements are having true. So this particular statement is translated in the first row. Now let's go for the general truth table of P implies Q. So when P is true and Q is false, we get false. For rest of the cases, we get true. Why are there two truth table for this? It is because when we say P implies Q, it is actually equivalent to not P or Q. Both the truth table will have the final column TFTT only. Here we are just using the negation of P and here it is just P. But here the operator is implies, but here the operator is disjunction. So when they say Q unless not P, it is actually this particular truth table. But what is this truth table doing? It is doing the work of implication operator. If this is going to be negation of P, then what is P value here? It is true and it is false. So what is this implication operator? When P is false, Q may be either true or false. But when P is true, Q must also be true. So they don't worry about the hypothesis being false. They can conclude it as true or false because the hypothesis itself is false. But when the hypothesis is true, it is some mandatory condition that the conclusion must be true. So that is the condition you have to remember here. In programming languages, when we say conditional statement, I'll just give you a pseudocode here. If there is going to be a condition x is equal to 1, then execute this block of statement, else execute this block of statements. This conditional statement is totally different from this logic. Logic conditional statement is what we call implication. So we actually call them as branching statement in other way in programming language, but this implication is not branching. This implication is based on hypothesis conclusion concept and not on programming languages. That's why I am specifying here. In programming languages, when they say if P then S, it means P is a proposition and S is a program segment. So S will be executed only when P is true and S is not executed when P is false. If this particular statement is going to be P and the block of statement is going to be S, only if P is going to be true, this S will be executed. When P is going to be false, this will not be executed. That is the case of programming languages conditional statement. But here implication is when it is false, it doesn't matter whether the conclusion is true or false. We know the conditional statement is P implies Q. From this, we will be able to take three other terms. One is converse, the other one is contrapositive, and other one is inverse. All these three are represented using the implication operator. But how? When we say P implies Q, it means if P is true, Q is true. What is the converse? It is like if Q is true, then P should also be true. This is converse. Just reversing the conclusion and hypothesis position, it becomes converse. What about contrapositive? It is the negation applied to the converse. So we have negation of Q implies negation of P. What is the contrapositive trying to tell you? If I say, if it is raining today, I will take an umbrella. When I say, if I am not taking umbrella, it means it is not raining today. Is this giving the meaning of P implies Q? Yes. From this we can understand contrapositive is equal to the original conditional statement. Now let's check for inverse. Inverse is applying negation to the conditional statement. We have negation of P and negation of Q with the implication operator. So let's see the truth table for better understanding. Here we have Q implies P. It means when Q is true, P should not be false. So here Q is true and P is false. So we get a false here. The rest of the rows will have true. So if you don't feel right with this particular truth table, you can go with Q, P and Q implies P. So what are the set of values you have to place for Q? It is true, false, true, false. The first true, false is for T and the second true, false is for F. Whenever Q is true, P should be true. So it is true. Whenever Q is true and P is false, we mark false here in the third row. What about Q is false? We don't worry at all. That's going to give you true anyway. So this will be Q implies P. What about negation of Q implies negation of P? Again, you have to start with negation of Q. Check where you have true in negation of Q. We have true in two places. Where do we get false in negation of P? We get here. So only this row will be giving you false. Have negative Q here, negative P here, then apply implies operator. When you have T here and F here, that is the case for F. Actually, you don't need to worry about whether Q is true, Q is false and all. Whatever comes in the place of hypothesis, when it is true, whatever comes in the place of conclusion, if it becomes false, then you should end up with false. So that's why I gave you the terms hypothesis and conclusion. So TFTT is the result of which particular table? It is the result of P implies Q. A conditional statement and its contrapositive are equivalent. So this is what I told you earlier. So what do we mean by the conditional statement? It is the original statement P implies Q. So we can otherwise say it as contrapositive is equivalent to the original statement. So here it is P implies Q. So when do we call equivalent? When two compound propositions always have the same truth value, we call them equivalent. For P implies Q also you have TTFF, then you have TFTF. Only the second row will have false, the remaining will have true. This is the same output column that you get here. What about the inverse truth table? So first we are negating P, FFTT, then we are negating Q, it's FT and FT. Negation of P is true here and the equivalent false of negation of Q is here. Only this row will be false. Where did you get the same answer? We got in Converse. The converse and the inverse of a conditional statement are also equivalent, but both of them are not equivalent to the original statement P implies Q. It means negation of P implies negation of Q is equivalent to Q implies P, and we know negation of Q implies negation of P is equivalent to P implies Q. In both the cases, inverse and the converse, they are not equivalent to P implies Q is what they say. These two go together, these two go together. Now we are getting into biconditionals. Let's take two propositions P and Q. Biconditional is actually by implication operator, we can say. The imply symbol will be applied in both the places. Implication we used a single side arrow. Here we will be using double side arrow. Again we will have true and false possibility. When it is true, when P and Q have the same truth value, it is true and it is false otherwise. Actually, which logical operation uses the reverse format? In exclusive OR, what happens? Whenever P and Q have the same value, it will be treated as false. Whenever P or Q have true, it is treated as true. But here the condition is just reverse. Whenever P and Q are going to have the same truth value, it is taken as true. Whenever they have different values, it is taken as false. P by implies Q is true when both P implies Q and Q implies P are true and is false otherwise. It means they are saying the conditional statement and the converse statement should be true. If P then Q, that should be true. At the same time, if Q then P, that should also be true. When both these implication statements are true, it is true. Otherwise, it is false. Biconditional statements are also called by implications because you are applying implication to both the sides. Just take the literal meaning. This is implies. This is also implies. You are implying it to both the sides. That's why it is by implies. Take it in that way. So what are the ways we can express this by implication operator? We can say P if and only if Q. So you can represent it using this particular statement, if and only if, or you can use it in mathematical way, IFF. Both actually mean the same. If is equal to if and only if. What is the other statement? P is necessary and sufficient for Q. If P then Q, and conversely. This is the conditional statement and this is the converse statement they are hinting. So anyway, if they say, it means it is by implication. Now we will see an example. You can take the flight is proposition P. You can buy a ticket is proposition Q. Now just apply it in biconditional. You can take the flight if and only if you buy a ticket. So in implication, we saw about negation of P or Q from Q unless negation of P. Here we are going to see about P implies Q and Q implies P. So let's take P implies Q. What is the truth value here? Only for this particular condition we will have F. Rest of the cases it is T. What about Q implies P? Only for this particular condition, T and F. So this has to be considered first and this to be the second. We have F here. Now we have to combine them using conjunction operator, that is AND. That is what they have given, both this one and this one. So this AND is placed here. When will we have true in AND? In conjunction. Only when both the cases are true, we will have true. So first row will have true and the final row will have true. The computation is between these two columns and not P and Q. Here we have F and T, T and F combination. So it is resulting in F. The biconditional statement is true when P and Q have the same truth value and is false otherwise. So from here what we can understand is when P and Q are having the same value, for the first row it is true and the final row it is false, the resulting column is giving true in both the places. So this is going to be the truth table. We will see for by implication, we are directly applying T and T to T and F and F to T here. The rest of the rows will be carrying false because only one of them are true at a time. Now we have seen about lots of logical operation like negation and or. In logical operation we also include implies operator, by implies operator. What is the precedence of those operator? The precedence order is given here. The top level will be the highest precedence and the bottom will be the lowest precedence. So when you find something like negation P or Q, what you have to do is first you have to negate P because it is carrying the highest precedence. After that you have to go for disjunction. So when conjunction and disjunction are there, give preference to conjunction. When you have disjunction and by implication, give preference to disjunction. Let's get into the practice problems of propositional logic. Which of these are propositions? What are the truth values of those that are propositions? So there are three columns. We have to check whether it's a proposition or not. In case if it's a proposition, we have to write the truth value. And what about the reason? In case if it is not a proposition, we have to list the reason why it is not. So let's start with 5 plus 7 is equal to 10. Is it a proposition? Yes, it's a proposition because you are just expressing some left hand side is equal to some right hand side. What is the truth value? 5 plus 7 will give you 12 actually, but here it is 10. So the truth value will be false. And what about the second statement? 2 plus 3 is equal to 5. When you add 2 and 3, you will definitely get 5. And so this is a proposition and the truth value is true. What about x plus 2 is equal to 11? Without knowing the value of x, you cannot come to a conclusion of true or false for this particular expression. So this is not a proposition. It contains a variable. The truth value will depend on the value that is assigned to x. In case if I say x is equal to 10, so 10 plus 2 will give you 12. Ultimately this will be false. In case if I say x is equal to 9, then 9 plus 2 will give you exactly 11. So the truth value will become true. Just based on the value assigned to x, the truth value will be depending on that. So this is not a proposition. Now the statement is answer this question. When they ask you to answer for a question, you cannot end up saying true or false. So this is also not a proposition and it does not assert anything, means it does not say some statement. You cannot conclude true or false. Here you can give some paragraph description only. Next question. Let P and Q be the prepositions. So the P preposition will be it is below freezing and the Q preposition will be it is snowing. Write these prepositions using P and Q and logical connectives. You can include negations also. When you write it in English, this will be like it is below freezing and snowing, but in general it is actually it is below freezing and it is snowing. So here this is P and this is Q and it is getting connected by and connective here. So what will be the expression? P conjunction operator and Q. What about the second one? It is below freezing but not snowing. So when you say it is snowing, it is Q. When we say it is not snowing, this becomes negation of Q. So here this is negation of Q. And you have a word called but here. What is this actually? But logically means the same as and. So in this case, it is below freezing is P and not snowing is negation of Q. So the logical expression will be P conjunction not Q. What about the third one? It is not below freezing. So here it is not below freezing. This will be negation of P. So here it is negation of P and it is conjunction. It is not snowing will be negation of Q. So it is negation P, conjunction, negation Q. What about the next one? It is either snowing or below freezing or both. You can have either or, like either first one is happening or second one is happening or even both can happen. This is definitely disjunction. So snowing is actually Q. Below freezing is actually P. When you translate in this way, it is Q or P. But regarding disjunction, whether it is P or Q or P, both are going to be same. So in that way, we can just keep it as P disjunction Q. Next, if it is below freezing, it is also snowing. Below freezing is P, also snowing is Q, but here it is connected using if. So when we say if P, Q, what it is? It is P implies Q. What about the next one? Either it is below freezing or it is snowing. So here it is P or Q here, but it is not snowing if it is below freezing. But it is actually and here. It is not snowing means it is negation of Q. If it is below freezing, it means P implies negation of Q. Either it is below freezing or it is snowing. This is one compound preposition and it is not snowing if it is below freezing point is another set of compound preposition. So you are connecting both these compound preposition using but. So P or Q for the first set and we have P implies negation of Q for the second set. So how will you rearrange this particular sentence? If it is below freezing, it is not snowing. So here snowing is Q, so not snowing is negation of Q. And you are combining both these sides using but. So but we know it is logically equivalent to and, so we are using conjunction operator. This is how you will be working with compound prepositions. The last statement, that it is below freezing is necessary and sufficient for it to be snowing. So we have told P is necessary and sufficient for Q. Which operation is it? It is biconditional. P is necessary and sufficient for Q. We know P is below freezing, Q is snowing. So it is P biimplies Q. Next problem, determine whether each of these conditional statements is true or false. What does implication operator mean? When P, the hypothesis, is false, Q, the conclusion may be true or false. If hypothesis is true, then conclusion must also be true. So here we know P, if it is false, Q can either be true or false. But once we know P is equal to true, definitely Q must also be true. If you find all these three conditions, you can end up with true. If you find the condition where P is true and Q is false, for that alone you will be marking the result as false. Now let's take every conditional statement and check. If 1 plus 1 is equal to 2, so this is actually P and this is actually Q. Is 1 plus 1 equal to 2? Yes. So P is true. Now we have to check 2 plus 2 is equal to 5. This is actually false. When P is true and Q is false, the result will be false. So here it is true, it is false, so the result will be false. What about the second conditional? 1 plus 1 is equal to 3. This is actually false. So P is false. 2 plus 2 is equal to 4. This is true. When the hypothesis is false, we are not worried about Q. We can mark it as true. Next, 1 plus 1 is equal to 3 is again false. 2 plus 2 is equal to 5 is also false. So we have false in P and false in Q. This will again give you true because we know when the hypothesis is false, we are not worried about the conclusion. If monkeys can fly, then 1 plus 1 is equal to 3. When they say monkeys can fly, can you imagine any monkey that has the capability of flying? No. So P is actually false here. Don't think only in terms of mathematical expression but also the logic behind the statement. When they say monkeys can fly, it is not possible. When they say birds can fly, it is definitely possible. So based on that possibility, you have to mark it as true or false. So when monkeys can fly, which is actually not correct, you can mark it as false. Once we know hypothesis is false, irrespective of Q, here we have false because 1 plus 1 is equal to 2. So irrespective of the Q value, we are going to mark it to be true. So only the first conditional statement where we had P is equal to true and Q is equal to false as the result of false. The rest of the statements are true. Next problem, given a conditional statement P implies Q. Find the converse of its inverse, converse of its converse and the converse of its contrapositive. Actually, we have to find the inverse, converse and contrapositive of P implies Q. Once you get the inverse, converse and contrapositive, for those value you have to find the converse. So what is the work of converse? Whatever is in the place of hypothesis will move to conclusion. Whatever is in the place of conclusion will move to the place of hypothesis under implies operator. Now we will find the converse of the conditional statement. So what is the converse? It is Q implies P. What is contrapositive? You have to apply negation to the converse variables. Negation Q implies negation P. What about inverse? You have to apply negation to the conditional statement. So it is negation P implies negation Q. So these three things you have to be very clear because you have to find the converse of inverse, converse of converse, converse of the contrapositive. Converse will replace the hypothesis and conclusion in the conditional statement. Now we have to find the converse of inverse. So we have to just replace these two and it will end up with negation of Q implies negation of P. Now converse of converse, just replace it this way, you will get P implies Q. What about converse of contrapositive? Just replace them. It is negation of P implies negation of Q. Equate them to the original statements and check. When you find the converse of inverse, it will give you the contrapositive statement. When you find the converse of converse, it will give you the conditional statement because if you take the conditional statement P implies Q, what is the converse? It is Q implies P. Now what is the converse of this particular expression? This will again give P implies Q, which is actually equal to the original statement. So this is how we are equating it. What about negation P implies negation Q? This is the inverse of the statement. Next question. State the converse, contrapositive and inverse of these conditional statements. If it snows today, I will sky tomorrow. So it snows today will be P and I will sky tomorrow will be Q. So let's remember this. P implies Q can be if P, Q, P only if Q, Q if P. It can be in any form. Why am I specifying this is when you have to state the converse, contrapositive and inverse, this particular statement has to be represented in other way. Now let's start with inverse. What you have to do in inverse, you have to just negate the proposition in the conditional statement. If it does not snow today, I will not sky tomorrow. So we are changing snow to not snow and sky to not sky. This is inverse. What about converse? So this is in the form of P only if Q. Now how should you change for converse? Q only if P. This will be equal to Q implies P and this is equivalent to P implies Q. Now you have to change it in this form. I will sky tomorrow only if it snows today. What about contrapositive? You have to negate this and put it in implication form. That is negation of Q implies negation of P. Now you can bring it to the form of if P and Q. So if negation of Q, then negation of P. What is Q here? I will sky tomorrow. So negation means if I do not sky tomorrow, then it will not have snowed today. So we are not getting into the grammatical part of English language. I am just trying to tell you that how prepositions change. That's all. Next statement. I come to class whenever there is going to be a quiz. So this is in the form of Q whenever P. So this is Q and this is P. Now we will just convert this to if P then Q form. So if we convert this way, what it will be? If there is going to be a quiz, I will come to the class. So this will be if P then Q. So from this you have to understand which is Q and which is P because we are going to work with that only now. We will get into the inverse. We have to negate P and negate Q. What is negation of P? If there is not going to be a quiz, negation of Q will be then I will not come to the class. So instead of don't, we will have it as won't. I will not or I won't come to the class. So this is inverse. You are directly applying negation to P and negation to Q. What about the converse? I have to just interchange this P and Q to if Q then P. What is Q here? I will come to class. So if I come to class, then there will be a quiz. This is actually equating to Q implies P. Here we have another way of expressing it. I come to class. This is Q only if there is going to be a quiz, which is P. Q only if P. Then there is an option P only if Q to represent P implies Q. Then when I say Q only if P, how will you represent this? So this is also expressed as Q implies P. This will be the converse. You can either go this way or this way, both are right. What about the contrapositive? You have to apply negation to the converse. If I do not come to class, then there will not be a quiz. I am just applying negation to Q and negation to P inside the implication operator. So this is if I don't come to class, then there will be no quiz. This is what the contrapositive statement is. Next statement, a positive integer is a prime only if it has no divisors other than 1 and itself. So this is P only if Q. There is a variable, a positive integer in this sentence, so technically it is not a preposition. Here they are not going to ask whether it is true or false. We are just going to find the inverse, converse and contrapositive statement. So for this case, we can treat it in the same way as we treat proposition. Now let's get into the inverse statement. If a positive integer is not prime, then it has divisors other than 1 and itself. So they have given it as no divisors. So you have to negate this no divisors. So it becomes it has a divisor. So don't take no divisor here as negation of Q and all. It will complicate the whole statement. So just take it has no divisors as Q and negate it and bring it to it has one divisor here. So this is negation P implies negation Q. What about the converse? When it is Q if P for implies operator, if I say P if Q, then it will be Q implies P. So here a positive integer is a prime if. So here it is one particular preposition if another preposition. Positive integer is a prime is actually P and it has no divisors other than 1 in itself is actually Q. So what is the form of P if Q? It is actually the converse of the statement. So we are expressing it in this way. You can write this as Q if P. Now what about the contrapositive? You have to insert negation here. If a positive integer has a divisor other than 1 and itself, this is if negation of Q, then it is not prime is negation of P. So this is exactly equivalent to negation of Q implies negation of P. So when they say no divisors as Q, it as a divisor becomes negation of Q similar to the inverse part. When they say it is a prime as P, not prime will be taken as negation of P. Next problem. Construct a truth table for each of these compound prepositions. So let's start with the first expression. So we have two operations here. One is exclusive OR and the other one is implication operator. So for exclusive OR, what is the condition? Whenever P and Q are having same value, it will be false. When they have different values, it will be true. This is XOR operation. What about implication? Under only one condition, you will have false. When the hypothesis is true and the conclusion is false, we mark as false. The rest of the places it is true. Now let's start working with P and Q. So what is P XOR Q? So the first row and the final row will have false and the remaining row will have true. So the first expression is actually done here. What about the second expression? We have to find negation of Q. What is negation of Q? Wherever you have T, you have to place F. Wherever you have F, you have to place T. Now you have to find P exclusive or negation of Q. So just consider only this column and this column. So T and F will give you T. T and T will give you false because T and T should give you false, F and F should give you false. What about F and F? Again it will give you false. What about F and T? It will give you true. So we have found T exclusive OR with negation of Q. Now the second expression is also done. What we have to do is we have to apply implies operator here. So for now, this is the hypothesis and this is the conclusion. Just check where you have true hypothesis and false conclusion. You have in two places here. You are going to mark false. The remaining places, irrespective of whether the conclusion is true or false, we know hypothesis is definitely false here. So this will be true. So the final value will be T, F, F, T. Next expression. So this question will not deal with implication. We are going with biimplication. So for this biimplication, whenever they have same value, it will end up with true. So TT and FF will give you true. Whenever they have different value, it will end up with false. Here you can find there were only two variables P and Q. But here there are P, Q, R, three variables. From this what you can understand is you have to extend it to 8 rows. So let's first take P, Q, R. Basically you can start with Q and R alone. T, 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 F, F, T, F, F. This will be the value for P is equal to true. T, 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 F, F, T, F, F. This will be for the false value of P. So we will start with the first expression P biimplies Q. Here you have true and true. So we will mark true. Then we have false and false here. So we will mark true here. It's TF, TF, FT and FT. Everything will be false. This is biimplication operation. What about the second expression? It is between negation of P and negation of R. So let's first negate P. So first 4 rows will have F and last 4 rows will have T. What about negation R? It's just an alternate of F and T instead of T and F. Now we have to find the by implication operator between these two columns. So what is F and F? It will give you true. F and F will give you true. T and T will give you true. T and T will give you true. The remaining places, FT will give false, FT will give false, TF will give false, TF will give false. Now we have to do XOR operation. This is actually P as of now and this is actually Q as of now. So this is in the format of P XOR Q. I am just equating it to this part so that it will be easy for you to work with it. Now whenever you find T and T, F and F, you have to mark false. Where you find T and T, you have T and T here. So this will be false. Then you have false, 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 false. So these two rows will have false. Last row is having true. So it will give you false. What about the remaining rows? T, F. So it is true. F, T, it is true. F, T, it is true. Then we have T, F, it is true. So this will be the final column. Next problem. Construct a truth table for P by implies Q, R by implies S, connected by implication again. Here you have 4 variables P, Q, R, S. For 3 variables you had 8 rows. Now since there are 4 variables, you will have 16 rows. It means first 8 rows of P will be for true value and last 8 rows of P will be for false value. First we will start with the by implication operator because all the operation is by implication. Whenever they have the same value, both the prepositions, you have to end up with true. When they have different values, you have to end up with false. So let's start with P, Q, R, S. Just start with the last 2 columns. You know TT, TF, FT and FF. So these 4 are for 2 variable. Just repeat them 4 times. Now for the first set of value you will have true. For the second set of value you will have false. For the next set of 4 values you will have true. For the next set of 4 value you will have false. This is how Q will be arranged. Now just go to P. For the first 8 rows you will have true. For the next 8 rows you will have false. Whatever way it gives you comfort, you can go with that way. Certain people will arrange like 8 and 8, then 4, 4, 4, 4, then 2, 2, 2, 2, then 1, 1, 1, 1. They will go in this order. That is also fine. Some people will be comfortable with 2 variable, then extend it to third and the 4th variable towards the left side. That is also fine. Whichever way you are comfortable, you can use. All you need to understand is you have to get 16 combinations for 4 variables. That's all. The first operation 1, 2, 3, 4. Then you have 5, 6, 7, 8. So all these 8 rows will have true value as per by implication operation. What about the rest of the values where you have T and F together? So everything will be false as per this particular table. Now let's get into the expression R by implies S. So here wherever you find true, TT is here, FF is here. So again TT and FF, then TT and FF, then TT and FF. Now treat this to be P and treat this to be Q. You have to find P by implies Q. Just find wherever you have TT and FF. This is TT, this is TT, you have FF here, then you have FF here, again you have TT here and TT here. The rest of the places you will have false. So 8 false rows and 8 true rows are there. So with this we are completing the content of propositional logic. I'll meet you in the next video. Thank you viewers.